Okay, welcome back. Today we'll start module 2, strings and exact matching in this course. And the topic for today is Z algorithm. We completed module 1 introduction in the last lecture, and in particularly in the last lecture we focused on the data structure warm-up. We looked at two data structures. One was for range minimum queries and the second was for bit vector rank operations. So this was to give you also a glimpse of the data structures that we'll be seeing in the subsequent classes. I also want to mention that these two data structures will be important for later concepts. So please make sure that you have very well understood these two data structures. So in the first data structure for range minimum query, we designed a data structure that was very similar to a binary search tree, and we saw that how it can efficiently answer the range minimum queries on one dimensional axis. In the second case, we looked at the data structure for bit vector rank operations, and the key feature of this data structure was that it supported fast order 1 queries, and the space requirements were asymptotically same as the input size. The general technique that we used here was that we divided the data into blocks and sometimes recursively. Then we stored the data at the block boundaries and handled the smallest blocks with lookup tables. So this lookup table, the use of lookup table, this technique we refer to as 4 Russians technique. So this finished the introduction module, and today we are going to move to the module 2, strings and exact matching. So in this module we will be specifically looking at the data structures and algorithms for exact pattern matching of biological sequences. And as you can imagine, when we are working with biological sequences, many of these problems can be framed as exact string matching problems. So that's why we are starting with the exact string matching module. For this particular lecture, we will be focusing on exact string pattern matching problem, and we will be solving this problem using Z algorithm. So in the string matching problems, or if you look at all the problems that involve strings, the exact string matching problem is the most fundamental problem. The description of the problem is as following. So you are given a string P, which is called the pattern. You are given a longer string T, which is called the text. The exact matching problem is to find all occurrences of pattern P in text T. Now I don't really have to motivate this problem why, for example, this is important. I am sure anyone who uses computers would know why this problem is important. For example, if you are working on a Word document and you just simply run a Control F command, or if you are working on a Linux system and you want to grep for certain pattern in a text file. So both of these are instances of the exact matching problem. So just to give a specific example, so suppose your pattern is ABA, and suppose you are given a text BBA, BAX, ABA, BAY. Then for this specific example, you can see that pattern P occurs in text T at locations 3, 7 and 9. So for this particular pattern, you can see that the pattern occurs at position number 3, position number 7 and position number 9. Note that two occurrences can also overlap. For example, this particular occurrence of ABA is overlapping with this particular occurrence of ABA. So given this problem definition, how do we solve this problem? Before going to the solutions, I also want to make a point that exact string matching is also important for biological sequences. For example, one major application where I would be using exact string matching would be that suppose you are given a pattern of DNA sequence. This pattern could be a single gene or a sequencing read coming out of a sequencing instrument, or it could be a short word of length k, which we typically refer to as k-mer in bioinformatics literature. And we would like to know whether this pattern occurs in a large reference genome sequence or not. So, for example, the reference genome sequence can be very long. As we saw in the introduction module, the human genome sequence is also 3 billion characters long. So, when working with the data of this scale, we are going to need efficient algorithms. I also want to describe basic terminology that we will be using in many problems involved with strings. So, recall that a string is a finite sequence of characters. For example, string Pondicherry is a string here. So, Pondicherry is composed of characters P, O, N, D and so on. We can denote a substring by this notation S interval I to j. So, we will refer to this as a substring of S that begins at position I and ends at position j. So, for example, in this Pondicherry string, cherry, so in this particular case in Pondicherry string, ditch is a substring. So, this particular substring starts at position 4 and ends at position 8. So, I can write this as S4. Also, if so, we will also use this word known as prefix. So, prefix is a special substring that ends at position I and it starts at position 1. So, it is a special substring that must start at position 1. So, we will denote a prefix as S12I. Similarly, a suffix is a special substring that must end at the last character of the string. So, we will denote a suffix as Si until the last character of S, and this is a suffix of S. So, again in the Pondicherry example, POND is a prefix and I can say that cherry is a suffix of this string. Also, an alphabet which we will typically denote as a symbol sigma denotes a set of symbols which are used to construct these strings. So, for example, I can say that the string Pondicherry is a string over alphabet A, B, C, D until Z. So, this is simply the English alphabet. Similarly, you can say that DNA sequences will be composed of alphabet of size 4 A, T, C and G. One disclaimer I also want to mention that in the bioinformatics literature, the terms string and sequence are used interchangeably. So, we sometimes may refer to as a sequence or we may sometimes use the word string in our lectures. Okay, so coming back to the exact string matching problem, again the problem is defined as given a text T of length m and a pattern P of length n. Find all occurrences of the pattern P in the text T, and we can safely assume that m is greater than or equal to n, because if m is less than n, then there is no occurrence of the pattern P in text T. So, what would be the naive algorithm to solve this problem, or because when we are starting to think about any problem, it is useful to think of what may be the easiest way to solve any problem. So, in this case, how would you design a naive solution for this problem? Well, the most naive solution that would come to mind is that I can start matching the pattern at the first position of the text and see whether all the characters of the pattern match to the text or not. So, in this case, I can start by matching the first character, second character, third character, fourth character and so on, until either I completely match all the characters or I see a mismatch, and then I would have to stop the search and move to the second position of the text. So, suppose there is a mismatch here, then I would subsequently move to the second position of the text and see whether the pattern matches at second position of the text or not. Similarly, I will repeat this process. So, maybe I will start matching one character at a time, and maybe the 5th character again is mismatching. So, this process can be repeated, and maybe at the 3rd position I may end up matching all the characters of the pattern, in which case I would say that the pattern has an occurrence in the text at position 3. You can see that in this algorithm we are iteratively checking for each position in the text, and for each position in the text we are spending at most order p time. So, you can immediately see that the runtime of this algorithm is going to be order text times order size of pattern. So, this is not the best way to solve this problem, and we have to look for faster solutions. What intuition can we use to derive a faster algorithm? Well, if you see, so suppose in the first iteration we find that the character A is mismatching, so we do not need to proceed further and we will move to the second iteration. Suppose in the second iteration we are able to match the 7 characters of the pattern, and here the 8th character is not matching. Observe that in the second iteration we already know some information about these next 6 characters of the pattern, because we know that these next 6 characters of the the next 6 characters of the text. So, here we have already passed through the next 6 characters of the text, and maybe we need to use that information to optimize the next iterations of the algorithm. For example, here you will see that the 1st and the 5th occurrence of the pattern is A. There is no A character in the middle. So, in the second iteration we already know that the 1st occurrence of the pattern matches at the 2nd location of the text, and the next occurrence of the A character is occurring at this position. So, there is no point matching the pattern at 3rd, 4th or 5th characters at all. So, an efficient algorithm would slide this pattern by more than 1. So, there is no point of repeating this 3rd iteration, because we already know that the next occurrence of A is at 6th position in the text, and we should slide the pattern all the way to the 6th position. So, that may be one intuition that efficient algorithms may use, is to not move the pattern one by one, but move the pattern more than once whenever possible. The next intuition that many of these algorithms use is that, observe that here the prefix of pattern ATG occurs again in the pattern. So, the characters 5th, 6th and 7th are also ATG. We know that from our iteration number 2 that the ATG pattern already aligned or already matched to the text. So, when we are working on this iteration we can even skip the first 3 characters, because we know that that particular part of the pattern would automatically match to the text, and we can even resume our character comparisons from the 4th position onwards. So, this could be another trick that could be used in the algorithms, is to know some information about the pattern and use that to skip some of the comparisons that the naive algorithm was doing. So, this is the intuition that is roughly followed in many of the known algorithms, but if we go to the details of these algorithms we will find that these algorithms differ in their details, but largely they are following this intuition that we just discussed in the last slide. It turns out that each of these algorithms require linear time, that is m plus n, where remember that m was the size of the text and n was the size of the pattern. Just looking at the history of these algorithms, so most of these algorithms for exact string matching problem were developed in 1970s. So Aho-Karasik algorithms, Boyer-Morse algorithms, KMP algorithm, these are some of the well known algorithms that were developed in 1970s. The algorithm that we are going to study in this lecture is the Z algorithm that was developed in 1996 by Dan Gusfield. Now each of these algorithms require order m plus n time for solving the exact pattern matching problem. One may wonder what was the need of this algorithm in 1996 when already the algorithms that have same time complexity already existed from 1970s. It turns out that Z algorithm is significantly simpler to understand and implement compared to the previous algorithms, and that is why I have chosen Z algorithm for teaching in this course. If you are suppose if you are doing competitive programming and you are looking for the fastest implementation, then a better choice may be Boyer-Morse algorithm. If you are using, for example, grep utility in Linux, the grep utility also implements Boyer-Morse algorithm because empirically it is faster than other versions of the algorithm. So empirically, because it uses sublinear comparisons, in most cases it ends up running faster, and that is why it is also used in the grep tool in Linux. Okay, but the focus in this lecture will be on the Z algorithm, and as I said, this is significantly simpler among all these algorithms, and so simplicity is always useful in the sense that we will be able to easily understand how this algorithm is working. Okay, so let us see how Z algorithm is helping us solving the exact string matching problem. Now the main ingredient of the Z algorithm is going to be this Z array. Let me define what do I mean by Z array. So suppose you have a string S. Array Z is defined in the following way, where each entry in this Z array, let's say Zi. So Zi should tell me the length of the longest substring of S that starts at position I and matches a prefix of S. So for example, at I position I need to know the longest substring that starts at position I and also matches the prefix of S. And we will define this Z array for all values of I ranging from 2 to size of S. Just to see an example, let us compute the Z values of the following example. As I said, Z array is only defined from position 2 onwards. So let us see what is the substring that starts at position 2, what is the longest substring that starts at position 2 and matches the prefix of S. So in this case, you will notice that the longest substring that starts at this position is actually of length 1, because only string of length 1, that is A, matches the prefix of S, which is A. So the substring of length 1 matches a prefix of S in this case. At position 3, note that there is no substring starting at this position matching as a prefix of S. So the Z value is 0. Similarly, at this position the Z value is 0 because there is no substring starting at this position that matches the prefix of S. At this position, at the next position, observe that the Z value is 3 because AAG substring matches the prefix of S. At the next position, again the Z value is 1. At the next position, the Z value is 0, it is again 0, then it is 2, then it is 1, and finally it is 0. So this, I hope the definition of Z array is clear to you by now, that it is the length of the longest. So Zi is defined as the length of the longest substring of S that starts at position I and matches a prefix of S. So let us see, so why are we focusing on Z array? For a second let us assume that there is a magic box that takes the input string and gives you the Z array. How would it help you to solve the exact pattern matching problem where the inputs were pattern P and text T? The simple trick is as following, that what we do is we simply concatenate the text and the pattern. So we would build a string S that would first have the pattern. We would put a splitter character. This is a special character that does not either occur pattern, so that should not occur in the pattern as well as the text. So it is a special symbol that we are using as a separator, and then we will put the text. So string S is a concatenation of the pattern and the text, and we have placed a separator symbol in the middle of the text and the pattern. What we are going to do is, for this concatenated string S, we are going to compute the Z values. And if you recall the definition of Z array, observe that the first observation that we have to make here is that Z I is always going to be less than equal to the length of the pattern for all I in 2 to size of the string S. This is because of the special separator symbol. Note that we can never have a situation where the substring of length greater than n matches a prefix of this string S, because this separator symbol only occurs once in the entire string S. So there can never be a situation where you have a long substring matching a prefix of S. So therefore all the values of Z will be always less than equal to n, which is the size of the pattern. The second property to note that here is that what we need to do for exact pattern matching problem is, once we compute the Z array, once this magic box gives us the Z array, all we need to check is where the value n occurs. So in this case, if the length of, so in this case n is equal to 8. So all we need to check is where this number 8 is occurring in this Z array, because that immediately tells us that there is a substring of length 8 that matches the prefix of string S, which means there is a substring in the text which matches the pattern. So all we need to do is to scan the entire Z array and check where the entry 8 occurs, or in this case, or in general, entry n occurs, right. So this gives an intuition of, if we have Z array, then solving the exact matching problem is trivial. That is, we just concatenate the pattern and the text, and we compute the Z array of the concatenated string and locate the values, just see the value wherever the value n is occurring, that immediately tells me that there is occurrence of the pattern in the text. So the importance of Z array is clear, that why we need to solve for this Z array. So in some sense I can solve the exact matching problem if I have access to an algorithm that computes the Z array. So the next obvious question now is, how do we compute Z array? So we can, let's consider it as a separate problem. Now suppose you have a string S and the goal is to compute Z array which has S minus 1 values. What would be the easiest algorithm to solve Z array? Well, the easiest algorithm might be that we just do a brute force search. So for example, if I am at position I can just do character comparison starting from position I to the character starting at position 1 of S, and just see how far I can get until I see a mismatch, and that immediately will give me the Zi value. Well, unfortunately, this algorithm, if we just do a brute force search, observe that this simple algorithm, if we do just brute force search of computing Zi by simply character comparisons, then for computing Zi we may be spending order S time in the worst case, and for the entire Z array we will end up spending order S square time in the worst case, which is actually not good, because we are, the whole point of looking for a better algorithm is to avoid quadratic runtime. So what can we do? What may be a better way to compute Z array that avoids this brute force character comparisons to compute Zi in this way? So here is the following intuition. So let us see what ideas can we use to accelerate Z array computation. Suppose for a second that we are computing these Z values one at a time. So suppose we started computing Z2, Z3, Z4, and let us say that we have all the values computed until Z119. Our current objective, let us say, is to compute the value of Z120. The question here is, can we use this previous Z values to compute the value of Z120? Let me give you one example to see how these previous values may help you. Let us consider an example where suppose Z101 is equal to 30, meaning that the longest substring that starts at position 101 and that matches the prefix of S as highlighted in green color, this substring has length 30. So suppose additionally I give you the information that Z20 is also 5. So meaning that there is the longest substring that starting at position 20 that matches the prefix of S is equal to 5. Can we say something about Z120 from the information I gave you? So if Z20 is equal to 5, observe that there is a string of length 5 matching as a prefix of S, and we also know that there is a mismatch at the 6th character. So the 6th character is mismatching. Because otherwise if it is a matching character, then Z20 would be greater than 5. So because Z20 is 5, we know that the 6th character is mismatching. Can we say something about Z120? Well, you can see that because this entire substring is identical to the prefix, and we can also see, so this information tells me that Z120 is actually equal to, so the character at position 120 is actually equal to the character at position 20 in S. So what I can do is in order to know the information of what may be the longest substring that matches from this position onwards, I can utilize the value of Z20. So because the first 5 characters I know here are matching the prefix, I can immediately infer that the first 5 characters of Z120 will also be matching the prefix, because these are identical to these and these are identical to these characters. And we also know that the 6th character onwards we have a mismatch. So therefore we can immediately tell that Z120 in this case must be equal to 5, because the 6th character onward it must be a mismatch because Z20 is also 5. So, the 6th character from position 20 was mismatching to the prefix. So, again the 6th character from position 120 will also mismatch to the prefix. So, this was one case where we can utilize the previous values. What about another case? Suppose I give you this information that instead, so suppose Z20 is now 15 instead of 5. Can we say something about Z120 in this case? Well, again if you apply the similar intuition last time, what it is telling you is that Z120, the first 15 characters are matching the prefix. From this information, what we can infer is that the first 10 characters starting at position 120, the first 10 characters must also be matching the prefix because of this match here. We cannot tell anything about the 11th character though, because we have no idea whether the 11th character is matching or not. In fact, 11th character is not matching. So, in this case the 11th character is not matching for Z101. So, therefore, we will have to move to the character comparisons and compare this particular character back to the prefix of S. So, what we can say in this case is Z120 must be at least greater than or equal to 10, and we can avoid the character comparisons of first 10 characters, and we can resume our character comparisons from the 11th character onwards, which will save us the time. So, observe that in first case we immediately got the value of Z120. In the second case we learned that Z120 is at least 10. So, we can resume our character comparisons from 11th character onwards. So, this is already giving you an intuition of how we can use the previous Z values to compute the subsequent Z values, and this intuition will help us develop a faster algorithm to solve the Z array. Let us formalize these ideas in the next slide. So, formally the algorithm will proceed as following. So, the first entry of the Z array, that is Z2, we will be solving using our Nye method, that is one character comparison at a time. So, we will compare the second character to the first character, then we compare third character to the second character, and so on. So, we will use the Nye method to compute Z2 and we will get the value of Z2. Now, assume inductively that the algorithm has correctly computed the values of Zi for I up to k minus 1. Our goal now will be to compute the value of Z array at position k. So, our goal is to now compute the values of Zk, given that we already have access to values Z2, Z3 until Zk minus 1. So, I need to define two notations here. So, one is L. So, suppose the way I am defining this ZL is, let us look at the values of Z2, Z3 until Zk minus 1. So, these are the substrings that are matching to the prefix of S. Among these substrings, suppose ZL substring is the one that extends farthest to the right. So, suppose ZL is a substring that extends farthest to the right and matching to the prefix of S. So, because observe that all these values of Z, I can denote them as a block. So, suppose this value particular here may be a block of this size, this value here may be a substring of this length, ZL in this case is a substring of this length that matches the prefix, and so on. Among all of them, let us look at the box that extends farthest to the right. So, in this case I am defining this notation L, So among these Z2, Z3, Zk minus 1, let ZL be the corresponding, let ZL be the value whose matching substring extends farthest to the right, and also let this rightmost position be R, right. So in this case ZL extends until position R. We will also denote this particular substring corresponding to ZL as alpha. So this substring that matches the prefix of S we will be denoting as alpha. Okay, so this L and R notations are going to be critical now. Suppose in the case 1 that the value of R is less than K, that is the K is the position at which we are computing the value of Z array. So Zk is what we are computing now, and suppose R is less than K. Then what we are going to do is we are going to follow the naive strategy to compute Zk, right. So in this case we will compute one character at a time, starting from position K of S, and we will start matching it to prefix and see how far we go further. So that is when if R is less than K. The case 2 is where we will save time, and that is when R is greater than or equal to K. So this is when we can pull some information from the previous Z values. So observe that ZL now extends until R, and R is greater than or equal to K. So then we have some information maybe that we can use to infer something about Zk. So here we have two following sub cases, right. So suppose, so now we have the case that R is greater than K. Let us consider the value of Zk dash, right. So K dash is basically in this case, so K dash corresponds to this interval. So K dash is equal to K minus L plus 1. So we are going to use value of Zk dash now, and we are going to check what is the value of Zk dash and how can we use it to infer the value of Zk. Observe that if Zk dash is less than beta, okay, I forgot to mention that we will denote the substring from K to R as beta. So this particular substring starting from position K until position R in S, this will be denoted as beta. So given this notation, let us see what is the value of Zk dash. If Zk dash is less than the value of beta or less than the size of beta, because beta is the string substring here. So if Zk dash is less than the size of beta, which means that the longest string starting at K dash that matches a prefix of S is shorter than beta. In this case we immediately know that Zk is equal to Zk dash, because this particular character which is after, so the first gamma characters are matching, this gamma plus 1th character is mismatching, right. So this gamma plus 1th character is mismatching, which also immediately tells me that this character will mismatch the prefix of S. So immediately we can set Zk as Zk dash. Now if Zk dash is greater than or equal to beta, which is the case 2b. So if Zk dash is greater than or equal to the length of the substring beta, as I am showing in the orange color, so Zk dash is greater than the length of the string beta. In this case what we know is that the first beta characters are matching to the prefix, but we need to do additional work from beta plus 1 onwards. So this position beta plus 1 onwards in this substring Zk starting at position K. So this I am denoting as 1, 2, 3 and so on. So beta plus 1 onwards is where we have to resume our character comparisons, because we know that the first beta characters are matching the prefix of S. In other words, I can also say that we have to compare the characters starting at position R plus 1 onwards, because until r we know that the characters are matching. R plus 1 onwards is where we have to do one character comparison at a time and see how far we can go on the right until we see a mismatch. So, accordingly, based on when we see a mismatch, we will set the value of zk dash, we will compute the value of zk accordingly, and we from this we know that zk will be at least greater than or equal to beta. So, and what exact value will this be will be informed by the character comparisons that we do here onwards. So, this completes the algorithm except one final detail is missing. We have said in the beginning that when computing zk, we were using these values of L and R, where ZL corresponds to the rightmost extending substring that matches the prefix of S. So, how do we immediately know the values of L and R? Well, we are going to follow the strategy that when we are computing the Z2, that is the first value of Z array, we will also compute L and R based on the value of Z2. So, if Z2 suppose is 3, then L will be set to 2 and R will be set to 4. In subsequent iterations, we will update the values of L and R because they will keep moving further towards the right. So, for example, observe that in case 2b, we started comparing characters beta plus 1 onwards. So, suppose the mismatch happened here, then in this particular case we will revise the value of L to k and R we will move further by 3 positions. So, R equal to R plus 3 because 3 characters have matched. So, this is how we are in each iteration we are also making sure that the values of L and R are also updated, so that the next iteration can use them. So, this completes the description of the algorithm that, and we can describe it as a lemma that given the values of Z2 until Zk minus 1 and we have access to the current values of L and R, the proposed algorithm computes Zk and also updates the values of L and R correctly. Let us look at the time complexity analysis. So, for computing Z2, Z3, so we are computing the Z2, Z3 until Zs one by one. So, that is clear. One way to analyze the time complexity may be to look at the time spent in each iteration. Observe that in each iteration we may in the worst case spend up to order S time. This is because in case 1, if this is the case, we still have to follow the naive strategy to compute Zk. So, unfortunately, if we analyze the algorithm in this style, we will end up back with the time complexity order S square. But this style of analysis is giving us a very loose bound because in actual this algorithm is running much faster. We have to use a different style to analyze this algorithm to get a tighter bound, and that will be as following. So, what we do is again we compute these Z2, Z3, Zs values one by one, that is obvious. What we are going to do to analyze the time complexity is to count the total number of matched and mismatched character comparisons throughout the entire algorithm. We will be counting them not iteration by iteration, but we will be counting them across the entire iterations. So, what is the sum of matching characters and what is the sum of mismatching characters comparisons in the entire algorithm? Observe that mismatch comparisons are no more than 1 per iteration, because as soon as we see a mismatch we stop the computation of value of that Zi. So, if we see in Zi, if we face a mismatch, then we move to the next iteration. So, at most we are having 1 mismatch comparison per iteration. Now, let us look at the match comparisons. How many match comparisons are we doing throughout the entire algorithm? Well, to do that, observe that in each match comparison we are also advancing the value of R towards right by 1 position. For example, as we just discussed here, if we have 3 character comparisons here, then we advance the value of r by 3 positions. So, whenever we are having match comparisons, we are advancing the value of r further towards right, but observe that the value of r can never exceed the size of the string s. So, therefore, the total count of match comparisons in the entire algorithm is bounded by order s. Similarly, the number of mismatch comparisons, because they are at most 1 per iteration, in the overall algorithm they are bounded by order s. The other trivial updates to update the value of L and R, those are order 1 updates. So, throughout what we can say is that the entire algorithm is spending order s time to compute the Z array from position 2 to the last position. So, to summarize this as a lemma, we can say that for a given string s, the proposed algorithm computes the Z array in order length of string s time. So, this style of analysis gave us a tighter bound, and what we can see from here, since we have a linear time algorithm to compute Z array, what we also have is a linear time algorithm to solve the exact pattern matching problem. Because recall that when we are solving the exact pattern matching problem, we are building the Z array of the concatenated string, and then we are solving the Z array for the concatenated string. So, if we are building the Z array in order s time, which is equivalent to order m plus n time, then all we need to do is to do a linear scan of the Z array and identify in what positions is the Zi equal to n. And we know that Zi equal to n if and only if the pattern occurs at position I minus n plus 1 of the text T. Because if there is a, suppose for example, if there is a, if this cell corresponds to n, then we know that inside the pattern, sorry, inside the text, the pattern has a match starting here. So, this summarizes the complete algorithm, that because we are able to compute Z array in linear time, we are also able to solve the exact pattern matching problem in linear time. So, given this algorithm, and also I have to emphasize that this is a simpler algorithm than Boyer-Morse or KMP algorithm, and this is the simplest algorithm that you can see in the literature, which solves the string matching problem in linear time. So, revise this algorithm, and in the future lectures we will see more string matching problems with more advanced data structures. Thank you.